today's lesson on abstract algebra, a fascinating branch of mathematics where we explore the hidden patterns and structures that make the world tick. Today, we're going to uncover the powerful concept of groups. Now, you might be wondering, what is a group? Well, in abstract algebra, groups are one of the most fundamental structures, and they help explain everything from simple operations to complex mathematical phenomena.
Before we jump into the nitty-gritty, let me ask you a question. Have you ever solved a puzzle? For example, a Rubik's Cube. You twist, turn, and rearrange. But no matter how many moves you make, there's an order to it all. Every action follows a rule, and there's a reason why the pieces always fall into place after a series of moves. This is what groups are all about. They're about patterns, order, and structure. Groups give us the rules that govern how things interact, whether they're numbers, shapes, or even abstract objects. Ready to discover the rules of these mathematical puzzles?
Alright, let's answer the big question. What is a group? In abstract algebra, a group is a mathematical structure that consists of a set paired with an operation that satisfies four key properties. Think of a group as a set of elements like numbers or shapes that follow a set of rules when combined with a specific operation. These rules give the set structure and order. So let's break down each of the four properties in more detail. Let's start with closure. In simple terms, closure means that if you take any two elements from the group and apply the operation to them, the result will always be another element in the same group. The set is closed under the operation. So for example, let's consider the set of integers under addition. Take two integers, say 3 and 4. If we add them together, 3 plus 4 is equal to 7. However, if we take the set of positive integers and consider division as the operation, then which is not an integer, meaning the set is not closed under division. Here's the key idea for closure. The result of combining any two elements using the group's operation must still be part of the same set. Next, we have associativity. This property says that the way you group elements when performing the operation doesn't matter. It will not affect the result. In other words, for any three elements in the group, the operation must satisfy the rule. The quantity of A plus B plus C is equal to A plus quantity of B plus A, because 5 plus negative 5 is equal to 0, and negative 7 plus 7 is equal to 0. In multiplication, the inverse of a number A is 1 over A, because multiplying a number by its reciprocal gives 1, which is the identity for multiplication. For example, 5 times 1/5 is equal to 1. Negative 7 times 1 over negative 7 is equal to 1. So, the inverse element undoes the effect of the original element, bringing us back to the identity element. With these properties, groups helps us understand how sets and operations interact, giving us a tool to explore more advanced concepts in mathematics. Whether you're dealing with numbers, shapes, or transformations, groups form the backbone of abstract algebra and many real-world applications.
For example number 2, non-zero real numbers under multiplication. Next, let's consider the set of non-zero real numbers under multiplication. We will denote the set as R is equal to R over 0. So let's check the 4 group properties. First is closure. Multiplying any two non-zero real numbers gives another non-zero real number. For example, 2 times 3 is equal to 6, which is an element of a real number. So multiplication is associative. The way we group numbers does not change the product. For example, quantity 2 times 3 is times 4 is equal to 2 times quantity 3 times 4 is equal to 24. Now the identity element. The multiplicative identity is 1 because multiplying by 1 doesn't change a number. For example, 5 times 1 is equal to 5 and 1 times 100 is equal to 100. Finally, the inverse property. Every non-zero number has a multiplicative inverse. For example, the inverse of 2 is 1/2 because 2 times 1/2 is equal to 1. All inverses are non-zero, so they stay in the set. Thus, the set of non-zero real numbers under multiplication forms a group because it satisfies all 4 properties: the closure, associativity, identity, and inverse.
Now that we've explored basic groups with integers and non-zero real numbers, let's move on to some moderate to challenging examples using real numbers only. These examples will test your understanding of the group properties, the closure, associativity, identity, and inverse. Now, let's take a closer look at positive real numbers. We'll denote the set as positive real numbers where x is an element of a real number such that x is greater than 0, and we'll consider multiplication as our operation. Let's examine the 4 groups properties one by one. First, the closure. This means if we multiply any two numbers from the set, the result should be also in the set. So if we take two numbers, say 2 and 3, their product is 6. Since 6 is also a positive real numbers, it satisfies the closure property. Next, the associativity. This property tells us that the way we group numbers during multiplication doesn't change the result. For example, the quantity of the product of 2 and 3 times 4 is equals to 2 times the quantity of the product 3 and 4 is equals to 24. So no matter how we group them, the product remains the same. So it satisfies the associativity property. Now the identity element. This is a number in the set that doesn't change other numbers when multiplied. Here the number 1 works perfectly because 1 times 5 is equals to 5 and 1 times 100 is equals to 100. So it satisfies the identity property. And now the inverse property. Every number in the set should have another number in the set that multiplies with it to give the identity. For instance, it as a real number, again, it's under multiplication. So let's go through the group properties to see if it forms a group. First, the closure. If we multiply any two numbers greater than 1, do we stay in the set? Yes. For example, 2 times 3 is 6. Since 6 is also greater than 1, closure holds true. So multiplication is always associative. The order of grouping does not matter. For example, the quantity of the product of 2 and 3 times 4 is equals to 2 times the quantity of the product 3 and 4 is equals to 24. But now, the multiplicative identity is 1. However, 1 is not greater than 1. So it's not our set. This means the set fails in the identity property, which is crucial for a group. Next, the inverse. If we take a number greater than 1, say 2, its inverse is 1/2. But 1/2 is not greater than 1, so it's not in the set. This means the inverse property also fails. So because of this set of real numbers greater than 1 fails in the property of both identity and inverse, we conclude that this set does not